This meeting is being recorded.
For problem 28 from chapter 15, we are given a carbon 13 NMR spectrum, the broadband decoupled spectrum. We're also given a depth 135 spectrum, and we're told that the depth 90 spectrum showed no signals. So we're asked to determine the structure of this compound, provided the spectra. So again, we were given the broadband decoupled and the depth 135, and we're also given one other bit of information, the molecular formula. So we can utilize that molecular formula to calculate first the hydrogen deficiency index. So I have my work shown down here for how I arrived at an HDI of 1. So this 1 degree of unsaturation, as you recall, could either be a double bond or a ring. So let's take a look at these spectra and see if we can figure out an appropriate structure for this compound. So first we see this one signal all the way down here above 200. And if you recall, I have our table down here. There's really only one signal that will see that high, and that's with a carbon of a carbonyl of either a aldehyde or a ketone. So that could explain our degree of unsaturation, that we have a carbonyl carbon in our compound. So we'll use that to guess, right, that we probably have a carbonyl somewhere in our compound. And we have, again, that degree of unsaturation satisfied. We have 4 signals in the range of 10 to 60 ppm. So this would represent 4 unique sp3 hybridized carbons here. So we have 4 unique sp3 carbons, right? And we can then use the depth 135 spectrum to further elaborate the structure of these. We see that 2 of the 135 signals are upside down. So if we look at our table down here, that would show us that if they are upside down, that would indicate a methylene group. Right, so these 2 here would be that of methylene groups. And let's see here. So based on the number of protons in our carbon, the other 2 signals must then be methyl groups, right? So we know that we have 10 protons total. We have only 4 used here with these 2 methylene groups. So that means that these 2 must be methyl groups, CH3s, to account for all 10 of our protons. So now that we know what our groups are, right, we have 2 CH3 groups, we have 2 CH groups, and then we have our carbonyl. We can start to construct our structure. And we know that we need some symmetry because we would have or rather, we need some lack of symmetry. So let's start to draw a proposed structure here and see if it makes sense. So say I proposed this structure here that had this high degree of symmetry. We would only produce 3 signals and not 4. So therefore, I know that I'm going to need to shift. I'll start my drawing up here. I'm going to have to shift my carbonyl slightly, but I still have those 2 methylene groups here, and then I have my 2 methyl groups here and my carbonyl. And this structure would make sense then to produce those 4 signals. So based again on all this information between our depth 135 and our broadband decoupled spectrum, this could be a proposed structure for our compound, this ketone shown